Welcome back to AI Paper Podcasts. We're continuing our special series on deep learning applications in medical imaging with a really foundational paper.
It really is, yeah.
Today we're tackling a 2017 study by Li et al. That honestly did a massive service for the entire field of breast cancer detection. It's all about the creation of the CBIS DDSM dataset.
And if you're an ML engineer who's ever worked in this space, you know the pain this paper solved.
Exactly. The mission here was, you could say, almost heroic. They took this incredibly valuable but totally inaccessible old data set and turned it into a modern, standardized benchmark. So today, we're unpacking how this curated data set finally gave the medical imaging community its own version of, say, an ImageNet, which is just a prerequisite for real progress.
That analogy to ImageNet is perfect. It really highlights how messy the field was before this. I mean, back in 2017, CAD systems, that's computer-aided detection and diagnosis, they were showing promise.
Right, the potential was there.
The potential was there, but they kept hitting these walls. For detection systems, CADE, the big problem was a really high false positive rate, a major clinical barrier.
And for the diagnosis systems, the CADX ones.
Well, despite years of research, none had really been approved for widespread clinical use yet. They just weren't reliable enough.
And the paper argues that the core reason for this wasn't necessarily a flaw in the algorithms themselves, but an infrastructure problem. The bottleneck was the data.
It was absolutely the data. If you look at the literature from before this paper, reproducibility was a nightmare.
I can believe it.
Researchers were using private internal data sets they couldn't share, or if they did use the main public resource, the old DDSM, they'd use these unspecified or sometimes even cherry-pick subsets.
So you could never really compare Model A to Model B.
Never. How could you claim your method was better? It made rigorous comparison, basically impossible. It just stalled everything.
And when you contrast that with what was happening in general computer vision, I mean, ImageNet, MNIST, MNIST, those open benchmarks were the fuel for the whole deep learning fire.
Exactly. Medical imaging desperately needed that common ground.
So the obvious candidate was this digital database for screening mammography, the DDSM.
Right. It had over 2,600 studies, a ton of data. But trying to actually use it was, it was a huge pain because of some very old technical hurdles.
Okay, so what were they?
So if you tried to work with the raw DDSM, you'd hit three big problems right away. First, the images were saved in this obsolete, non-standard format called LJPEG.
LJPEG, not standard JPEG.
Nope, lossless JPEG. But a version that nothing supports anymore, so just getting the pixel data was a project. Second, the decompression tool you needed, this thing called the Stanford PVRG JPEG codec, was last updated in 1993.
1993, wow, okay.
Yeah, trying to get that vintage C code to compile on a modern Mac or Linux box was like an exercise in digital archaeology.
I can't even imagine the frustration. You're trying to solve cancer detection, and you're stuck fighting with a compiler from 3 decades ago.
Many people just gave up. But the third problem was maybe the most critical, the annotation quality.
Right, the labels.
The original ROI, or region of interest annotations, were just general locations. They'd give you a wide outline and say, the mass is somewhere in here.
Not a precise segmentation.
Not at all. So every single research group had to write their own segmentation algorithm first, just to get started. And if everyone's pre-processing is different, your comparisons are invalid from the get-go.
Okay, so this sets the stage perfectly for CDIS DDSM, the curated breast imaging subset of DDSM. This is the fix, the debugged, standardized, modern version.
That's the goal.
And the scale of the curation is pretty significant. They didn't just convert everything. They focused on a high-quality subset, right?
Yes, they curated 753 calcification cases and 891 mass cases. And for every single one, they provide verified pathology information, normal, benign, or malignant. That's fundamental.
And crucially, they included the BI-RADIS assessment. Can you explain what that is for our listeners who might not be in the medical field?
Sure. BI-RAD is the Breast Imaging Reporting and Data System. It's a standardized scale radiologists use globally. It goes from Category 1, which is normal, all the way up to Category 6, a known biopsy-proven malignancy.
So having that metadata allows models to learn the different degrees of suspicion, just like a human radiologist would.
Exactly. It makes the data set so much more clinically relevant.
All right, let's get into the technical weeds here. The first huge task was just cracking open those LJPEG files.
Yeah, the decompression.
The authors didn't just find some old tool. They had to actually modify that 1993 codec just to get it to compile on a modern OS.
A huge effort.
And once they got the raw binary data out, they used Python tools to convert it first to a 16-bit TIFF file and then finally into DICOM.
And that conversion to DICOM, the standard for medical images, is key for usability. But the most important detail for any data scientist listening is that they confirmed the entire process was completely lossless.
So no data degradation. You're getting the original high-fidelity pixel data just in a modern package.
Precisely. They preserved everything. Then, beyond just decompression, they standardized the data processing. The original DDSM tools were all in, like, old bash scripts in C.
Not exactly portable.
Not at all. So they re-implemented everything in cross-platform Python. This makes the whole pipeline transparent, and you can replicate it anywhere.
That's vital for reproducibility. They also standardized the pixel values themselves.
Yep. They converted the raw pixel data to standardized 64-bit optical density values, then remapped that to 16-bit. They did apply a standard noise reduction clipping.
But, and I love this part, they included a flag to turn the clipping off.
Right.
You can get the original raw values if you need them for some kind of specialized research. That's just great foresight.
It really is. And you can't overlook the manual cleaning. A trained mammographer went through the images.
What did they find?
They ended up removing 339 images, a pretty significant number. These were cases where the data file said there was a mass, but when you actually looked at the image, the lesion just wasn't clearly visible.
So basically just noisy labels. Getting rid of that cleans up the data set immensely for supervised learning.
A huge improvement in data integrity.
Okay, so now we get to what I think is the crux of the paper for CADX, or diagnosis researchers, improving the segmentation. Mass, shape, and margin are huge indicators for malignancy, so getting that ROI right is everything.
Absolutely paramount. And remember, the original DDSM outlines were just these imprecise, wide scribbles.
So how did they fix it?
They focused specifically on the masses, and they used a really sophisticated iterative technique. It's a modification of the local level set framework.
Specifically the Chan and Vase model, right?
That's the one. You can think of it as an algorithm that starts with the original bad outline and then sort of evolves it. It shrinks or grows the contour until it snaps perfectly to the true boundary of the mass based on the image intensity. It's a really elegant solution.
And they didn't just say it was better, they proved it. This is where the validation numbers get really impressive. They compared their new automated segmentations against a gold standard, hand-drawn by an expert radiologist.
Right, using the Dice coefficient.
And for anyone who doesn't use it daily, the Dice coefficient is just a measure of overlap. 0 means no overlap. 1 means a perfect match.
And the results were, well, staggering. The mean Dice for the original DDSM outlines against the gold standard was just 0.398.
0.398, so less than 40% overlap. That's pretty bad.
It's basically useless for training a precise model. But they're new automated segmentations.
Yeah.
The mean Dice score jumped to 0.792.
Wow, so from 0.4 to almost 0.8, they effectively doubled the segmentation accuracy.
A massive jump. And it was statistically significant with a p-value that was just astronomically small. It proved that CBIS DDSM isn't just cleaner, it's quantifiably more accurate.
That improvement is huge, but, 0.792 is still not 1.0. Given how critical those mass margins are, did the authors talk about the failure modes? Was it the algorithm's fault or something else?
That's a great question, and they did address it. The failures weren't really from the algorithm itself, they came from the images.
Meaning?
Lesions with really ill-defined or obscured margins, the ones that are really tough for a human radiologist to see a clear border on, that's where the Dice score would drop. The model struggles where the human struggles.
I see. So the accuracy is still bounded by the biological reality of the lesion and the quality of the image.
Exactly, which tells us where we need to focus next on specialized techniques for those inherently difficult cases.
That makes sense. Okay, let's talk about structure. For deep learning, how the data is organized is almost as important as the data itself. They made a training and testing split.
Right, 20% for testing, but it wasn't just a random split, and this is key.
It was stratified.
Yes. Stratified based on two critical things. The pathology, so benign versus malignant, and that BI rate assessment we talked about earlier.
Why is that so important?
It ensures that your training set and your test set have an equal distribution of easy, medium, and hard cases. You don't want your test set to accidentally be full of obvious, easy-to-classify cancers, because then your performance metrics will look inflated.
Right, you need to make sure the test set is just as challenging as the training set to get a true measure of performance.
You're guaranteeing a fair, balanced evaluation of the model's capabilities.
And for ease of use, they packaged everything really nicely. You get the full mammograms, the binary mask images for the ROI.
And super conveniently, pre-cropped images of just the abnormality saves a ton of boilerplate coding.
For sure. And beyond the images themselves, all that rich metadata is in simple CSV files. I was looking at the subtlety rating, the original radiologist's difficulty rating from 1 to 5.
That subtlety rating is gold for a researcher. You can use it to weight your training or to specifically analyze why your model is failing on cases that a human expert also found difficult.
Plus, you have all the specific descriptors, mass, shape, margin type. It allows you to build models that can learn the same nuanced language radiologists use.
And to close the loop on the whole transparency goal, the entire Python code base they use to generate the dataset is public on GitHub.
Which is the ultimate fix for that reproducibility crisis they set out to solve.
Exactly.
So, to sum it all up, CBIS DDSM took this invaluable but technically inert historical resource and turned it into a proper modern benchmark. It finally allowed for fair head-to-head comparisons of CAD algorithms.
It absolutely accelerated progress.
And as a final thought for you, our listeners, to take away something to chew on.
Go on.
Even with this massive leap in data quality, the authors still found a performance limit, and it was tied directly to breast tissue density.
Ah, yes, the BIR as density 4 cases.
Exactly.
Yeah.
They noted that the segmentation accuracy tends to decrease significantly in extremely dense breasts.
It tells us that even after you fix the data access and the annotation problems, the underlying biological challenge remains. A mass in dense tissue is just fundamentally harder to see.
So the question for future research, the real frontier is, what now?
The question is, how do we build models that are specifically designed for that challenge? Do we need multi-view data fusion or specialized image enhancement just for those BIRAS4 cases that still limit the real-world performance of these amazing systems?
A truly challenging problem that builds directly on the incredible foundation Lee and his team provided. Thank you so much for walking us through this essential paper.
My pleasure.
We'll be back soon with more from our AI Paper Podcast series, digging into the latest research.